A new wave of observations is pouring in, and with every passing day the mystery of the interstellar comet 3I/Atlas is deepening. Fresh images released this week reveal dramatic changes in the object as it moves toward its closest approach to Earth. Although scientists are beginning to form better hypotheses about its nature, the behavior of this comet continues to defy expectations. What follows is a complete breakdown of what is currently known about 3I/Atlas as it accelerates through the inner solar system on a trajectory unlike anything seen before. The comet will make its closest pass to Earth on December 19th, only a short time after its perihelion on October 29th, when it received the most intense solar radiation of its journey. Before and during that perihelion, it was struck by multiple solar storms, injecting even more energy into its surface and coma. Since its discovery in early July, and after tracking it back through older sky surveys, researchers have been closely monitoring its evolution as it transitioned from the near void of interstellar space into the energetic environment near our Sun. Out there, far from any star, it would have received only the faintest background radiation, essentially cosmic rays and scattered galactic photons. Near the Sun, however, the intensity jumps to hundreds of watts per square meter, a radical shift for any frozen interstellar wanderer. Based on orbital reconstructions and comparisons against the Gaia All-Sky Stellar Catalog, 3I/Atlas has not passed near any star for at least 10 million years. For all practical purposes, this is the first time it has encountered the inner region of a stellar system in a very long time. That is why the anomalies observed over the past several months are so fascinating. One of the most significant developments has been the emergence of a sunward-facing tail, a structure rarely seen in comets. As the main antisolar tail has begun to fade post-perihelion, this sunward jet has become brighter and larger, indicating unusual plasma or magnetic interactions. Early in its approach, spectroscopic studies revealed the comet's molecular composition. But the real surprise came near $2.50, when 3I/Atlas suddenly brightened by 2 full magnitudes. That kind of long-lived brightening is not typical. Comets may experience brief outbursts, but this object maintained and even increased its luminosity thereafter. The leading hypothesis is that global cryovolcanism occurred, an event in which volatile ices sublimate across the entire surface rather than in isolated vents. The closest analogues within the solar system are certain rare carbon-rich asteroids and trans-Neptunian objects that exhibit similar spectral fingerprints. These bodies contain metallic grains, water-bearing minerals, and organic residues formed far beyond the protoplanetary disk. When heated for the first time in millions of years, they can undergo catalytic transformations. In particular, the formation of magnetite crystals, Fe3O4, is a key indicator of such processes. As magnetite develops, the object can begin generating a stronger intrinsic magnetic field in addition to the induced plasma magnetic field that forms around the coma. Recent laboratory studies of returned asteroid samples have shown that these types of objects often contain the foundational ingredients of life: amino acids, simple sugars, nucleobases, and complex organic chains. If such compounds are common on metal-rich carbonaceous bodies, then an interstellar comet like 3I/Atlas, exposed to billions of years of cosmic radiation and enriched with volatiles, may also carry these precursors. The unusually high CO2 to H2O ratio measured around the comet, nearly an 8-to-1 deviation from typical solar system comets, further suggests long-term chemical processing in deep space rather than by repeated solar passes. The sudden activation at $2.50 aligns with theoretical models showing that liquid water can transiently exist within porous icy strata at that distance under sufficient internal pressure. If liquid water formed, even briefly, catalytic reactions could have rapidly produced magnetite, additional organic molecules, and jets of vapor, consistent with the brightening and the enormous 50,000-kilometer plumes observed after perihelion. The comet rotates every 16 hours, which means solar heating would be distributed fairly evenly across its surface. This supports the idea of a global event rather than a localized flare. Over long interstellar timescales, an insulating crust of complex organics and processed ices could accumulate. When suddenly heated by solar radiation, that outer shell would vaporize rapidly and uniformly. Chemical measurements of the coma showed elevated nickel-to-iron ratios, a signature resembling certain rare meteorite classes believed to have formed outside the Sun's protoplanetary disk. Such materials can act as catalysts for reactions that produce more complex organics. If 3I/Atlas followed a similar evolutionary path, it may be carrying an archive of prebiotic chemistry forged in another stellar system entirely. As 3I/Atlas continues outward after passing Earth, it will head toward a relatively close encounter with Jupiter in March, though not close enough to be captured. By early spring, Earth will pass through the region of space the comet occupied during its perihelion. Any dust or residual material released by its massive cryovolcanic jets could drift into Earth's atmospheric envelope. Whether this results in visible meteor activity or microscopic deposition of exotic organics remains unknown. New images taken in early December reveal that the sunward-facing jet is expanding even as the comet dims overall. This structure appears dense, bright, and sharply defined, unusual traits that suggest strong magnetic or plasma dynamics. The antisolar tail, by contrast, is growing more diffuse. Such asymmetry is not typical and could provide the key to understanding how interstellar objects interact with the heliospheric environment. The following timeline summarizes the most likely sequence of events based on current observations.